right. Well, it is good to see everybody. Did you have a good 3-day weekend? Okay, very cool. Let's see here. Okay, so Caleb, I'm going to put you out in the hallway and have you take your quiz for me, sir. So I'll give you 20 minutes on that. And you can use a calculator if you'd like to. I got those right over here. There you go. All right. Calculator's right there, sir. Okay, as for everybody else, I've only got a few housekeeping items, but one of them is incredibly important. On Thursday, we're going to be taking our first exam. So we want to be looking ahead to that. I passed out on Friday those 3x5 note cards. Hopefully, you've already started writing some information that you feel could be useful to you. But it's going to cover the 3 lessons we've had so far: the right triangle trig, angles and their measures, and then what we did last week, unit circle and evaluating on the unit circle, evaluating trig functions. Okay, so definitely, if you have any questions, come on in. I'm here after school today. Unfortunately, no tutorials tomorrow morning because it's a late start Wednesday, but I'm here after school again if you have any questions. And then this Friday by 8:05, that is the deadline if you want to retake angles and their measures, that quiz from last week. Just like always, you have to have the angles and the measures assignment completed and turned in before you go ahead and retake. Okay, as far as this week goes, it should be pretty straightforward. Today and tomorrow, I'm going to go ahead and start showing you how to graph sine and cosine. And then we'll take our test on Thursday, and we'll talk about it on Friday. Sine and cosine graphing is not on the test tomorrow, just those 3 that I mentioned. Okay, so a couple things before we go ahead and get started. It has been a 3-day weekend, but again, I want to go ahead and make sure that we're all on the same page. Be on time, grab any materials provided on the front bookshelf, be in your seat and ready to begin when the bell rings. Follow directions and be listening for important information. You folks have been doing an amazing job, especially with the electronics. Okay, remember, we cannot have any of that in. I've seen a few earbuds now and then, but we need to go ahead and make sure those are out. The only thing I would really say that all of the classes need to work on, I have a lot of people who are taking longer on the bathroom visits than they need to. So I've been reporting a lot of people. So please be mindful of that, especially if we have other people that need to go to the bathroom. You got 7 minutes. Okay, plenty of time. Okay, go ahead and just take care of your business. Come on back. And we'll go from there. Because if it happens to be too many times for one person getting, over that 7-minute mark, and I got to keep reporting you, well, you just won't go to the bathroom anymore. Okay, that'd be super easy on me. All right, questions. All right. Well, here's what we're going to do. If you will go ahead and pull out a sheet of paper for me. Right after we did that. Let's wait until after we do this. Okay, pull out a sheet of paper, please. I've got scrap paper up here if anybody would like to grab some. Scrap paper over there. Okay. All right, so it's been a long weekend, so I want to go ahead and practice what we were doing at the end of last week, evaluating trig functions on the unit circle. So I'm going to give you an angle measure. I'm going to give you 4 minutes. I'm going to want you to diagram the triangle after sketching the angle, and then evaluate all 6 of the trig functions at that location. Okay, so here we go. Your angle is 5 pi over 3. Okay. Remember to simplify, rationalize if necessary. Okay. And then we'll talk about it once we're done. 5/3 pi. minute 50. "45 seconds." Okay, that's 4 minutes. Let's go ahead and talk about it. What quadrant is 5/3 pi in? Ooh, not quadrant 3. Quadrant 4. Okay, so let's say I go around here. Probably going to look maybe something like this. Okay, so this is 5 pi over 3. Remember, if it's a mixed number, you can rewrite it as a what? Oh, I already said it. If it's an improper fraction, you can rewrite it as a mixed number. So 5 pi over 3, that's going to be 1 2/3 pi. Okay, so that's definitely going to put me in the fourth quadrant. Remember, that's step 1. Go ahead and sketch the angle. Okay, now bless you. Using that angle, I'm going to create a what? Okay, a right triangle. We're always going to connect it perpendicular to the closest x-axis. Now, this right here, this has to be one of those two special right triangles that we were talking about last week, the 30-60 or the 45-45. This one is the 30-60. Now, there's a couple of ways you could do this. You could take the closest x-axis, 2 pi. You could do a little bit of algebra. Go ahead and subtract the 2. Okay, and what you're going to end up with is pi over 3. Did anybody want me to run through the algebra and show that? Good on that. Okay. Another way you could have done it is to look at the mixed number. See, I already rotated 1 pi, which is half a revolution. So if I had to rotate an additional 2/3, how many more thirds will give me a whole? Okay, just 1/3 pi. So this would be pi over 3. That means that this is pi over 6. Okay. Now, I'm really encouraging you to make sure you're familiar with those radian measures when it comes to 30, 45, and 60. But if you want to use the degrees right now, that's okay. Remember, pi over 3, that was 60 degrees. This one's 30. So now I know what triangle, I know exactly what my 3 side lengths are. I know the hypotenuse is 1 because we're on the unit circle. Okay. Can anybody help me? What was across from 30? What was that fraction? 1/2. And what was across from 60? Root 3 over 2. Yes, and it would be negative because y's are negative in quadrant 4. Okay, so this is the triangle that we should have come up with. And then looking at each of the 6 trig functions, you've got your radius, you've got your y, and you've got your x. So this is what we should be getting. Okay. Sine of 5/3 pi should be negative root 3 over 2. The reciprocal cosecant should be negative 2 root 3 over 3, and then all the way through. Okay. Remember, always simplify and rationalize if necessary. That means remove a radical from the denominator. Okay. Did anybody want me to look at one specifically? Like how we got one of those answers? Everybody's okay with that? Okay. Well, how did we do overall? How many people got 6 of those? That's good. That's the most hands so far. Okay. What about 5? 4? Okay. All right. Well, remember, this is something that we're going to continue to practice. So I'm going to go ahead and tell you, we're going to do this again sometime this week. I'm going to give you another angle. You're going to run through all 6 of the trig functions. The next one will be for a grade. Okay. So there's only 2 days we can do that because Thursday's the test. It's either going to be tomorrow or it's going to be on Friday. One of those 2, we're going to be doing something like this. Okay. So questions. Okay, fantastic. Good. Let me go ahead and erase this, and we're ready to start. Let's go ahead and take a look at sine and cosine. Okay. All right, so the graphs of sine and cosine functions are periodic. So what that means is they're going to repeat themselves over and over again. We need a certain number of radians for that to happen. Okay, what you're going to find out for sine and cosine, their periods are 2 pi radians. Okay, so every 1 revolution, you've got another section of the graph. Kind of think about if I had a rubber stamp and I just kept stamping the same thing over and over again. That's exactly what's going to happen. That'll make more sense in just a moment. Okay. Now, the sine value of a function is equal to the y value at the corresponding point or angle on the unit circle. Also, the cosine value is equal to the x value at the same point on the angle. Remember, that's just reinforcing what we did last week. Sine is the y variable, cosine is the x variable. Okay. Well, here's how we're going to do this. Every ordered pair, xy, that we're accustomed to, it's now going to look like this. The x's are going to be your angle measures, and it doesn't matter if it's degrees or radians. We're going to be working with radians, though. And then the y value is going to be your ratio. In fact, if you look at the grid we have right here, it is an xy coordinate plane. The only difference is that horizontally, you've got radian measures. So that's what we're going to be using here. Okay, so in example 1, since the graph will complete 1 full cycle on the interval from 0 to 2 pi, the period of sine of x is 2 pi. Now, you remember way back in the day when you were first learning about linear functions and quadratic and all that good stuff, a lot of times you probably created a table. You plugged in values of x, you got the y values, and then you had points you could connect. But we're going to do the exact same thing here. Remember, everything about these graphs, where do you think it's coming from? What did we learn last week? The unit circle, okay. So let's take a look. I've already got sine with a bunch of radian measures plugged in, 0, pi over 2, pi. But you'll notice it's only the axes, the x and the y axis values. Anybody remember what we call those? If you stop rotating on an axis, it was a big word, started with a Q. Quadrantal. So we're only using the quadrantal values. Well, let's go ahead and get some ordered pairs, because here is what sine is going to look like. It's going to be that repeating over and over again. But how do we get that curve? Okay, well, let's take a look. Well, remember that sine of theta, can anybody remind me, what's its ratio? It's y over r, right? Everybody agrees? But remember, we're on the unit circle, where the radius is what? Where the radius is 1. So y divided by 1, that's just y. So at every one of these angle locations, all I want is the y value from that ordered pair. So for example, let's say I want sine of 0 radians. Okay, so here's 0 radians. Well, there's the ordered pair. Since we know that sine is y, the y value of 0, so sine of 0 should be 0. See, both of those are working together to give me a point on the graph. So 0 radians gives me a ratio of 0. And now we're going to work our way around the unit circle. Okay. Lexa, do me a favor. Go ahead and shut that Chrome. Okay. Appreciate that. So at pi over 2, we have this right here. So somebody help me out. What's sine of pi over 2? Well, that's the point at the location. Remember, sine represents what? X or y. So what's the y value at that location? So sine of pi over 2 equals 1. So my next ordered pair would be pi over 2, comma 1. Okay, so I'm using the unit circle all the way around. Let's do the next one. What's sine of pi? What's the y value at pi radians? 0. So now I have the ordered pair pi 0. Okay. What's sine of 3 pi over 2? Negative 1. So that's why I have 3 pi over 2, negative 1, and finally 2 pi, which is coterminal with 0 radians. Okay. Sine of 2 pi would also give me 0. So we have 2 pi 0. Okay. Well, let's go ahead and plot these. Now, it's just the same as you would plot on any other coordinate plane. Okay. We start at the origin, so there's 0, 0. Then we have the ordered pair pi over 2, 1. So from the origin, we're going to go pi over 2 to the right, and then 1 up. Okay. Let's see. Then we have pi comma 0. Then we have 3 pi over 2, negative 1. And what was 2 pi again? 2 pi was 0. So now if I go ahead and connect these with a smooth curve, there is the graph that I was referring to. There we go. That's what one parent of sine looks like. Okay. Now, you remember how I said I had like a rubber stamp and it was just going to repeat itself over and over again? Okay. Well, every time I rotate, I'm going to get something that looks like this. So this represents one rotation around the unit circle. If I were to go ahead and rotate again, well, then it's going to go ahead and give me another period of the graph. Okay. So how many times can I rotate? Remember, an infinite number. Every rotation is going to be another period, another section of this graph. I could also rotate clockwise. If I started here, rotated clockwise around, that's going to go ahead and give me another section and a period in the other direction. So that's what I was referring to a moment ago. It's just the same thing over and over and over forever. Okay. Now, these 5 points, these are going to be super, super important to us because eventually we're going to be using these points to help me transform these. Right, Noah? Right. Okay. So we've got 3 zeros. If it's crossing the x-axis, we're going to call that a 0. That's a 0, 0, and that's a 0. What do you think this point right here is? Starts with an M. It's the largest element of the range. Maximum. So we're going to call it a max. So what do you think this one down here is going to be? That's the minimum. Okay. Sine's parent will always start at the origin. Now notice I said parent, because once we go ahead and start transforming these, then it could start anywhere. Okay. All right. So any questions about how I got that graph? That's not too bad, right? Yeah. Sure. Right there. Okay, so now let's go ahead and dive a little deeper. Let's find out a little more about sine of theta. Okay, go ahead and make sure he has time to copy that. Okay, so I went ahead and provided this for you so that we could just talk about it and you already had it copied, but the domain is all reals. Okay, the more I rotate, the more of the graph I actually have. Okay, the range has to be between -1 and 1. Well, if you come back over here to the unit circle, okay, take a look at all of these ordered pairs that we have here. What is the single largest y value that we got? 1. What's the single smallest y value? -1. So that's why the range has to be between -1 and 1. Everything we know about these graphs is coming straight off the unit circle. Okay, now I've got x-intercepts, maximums, and minimums all highlighted. Okay, because think about it, if this graph repeats forever, how many x-intercepts am I going to have? I'm going to have an infinite number. How many maximums and minimums? I'm going to have an infinite number of those. So these are providing you little formulas. Oop, where did I put that? Hello, sir. That's time. So these little formulas are just providing you a way to go ahead and find specific locations for each of those. Does anybody want me to show you one just to see how it works? Yeah, okay. Let's say a maximum. Let's say I want to go ahead and start finding maximums. So the formula is pi over 2 plus 2 pi k, comma 1, where k is an integer. And here's your set of integers, just in case you forgot. The very first counting numbers you were ever taught, okay, the positives right there, 0 and their negatives. That's what the integers are. Okay, so let me come on back over here. Let me go ahead and start to plug in some values. So here was my formula, pi over 2. Oh, if you'll put it in the tray, please, sir. Pi over 2 plus 2 pi k, comma 1. Okay, so let's start with k equals 0. Okay. Well, all I'm going to do is plug in because it's providing me a formula. So pi over 2 plus 2 pi times 0. Well, what's 0 times anything? 0. So if that disappears, I've got pi over 2, so this is telling me that there's a maximum at pi over 2, 1. See, isn't that the very first maximum that we ever saw? Let's plug in another one. Let's plug in k equals 1. Okay, so that would be pi over 2 plus 2 pi times 1. Well, if you go ahead and do the algebra here, you end up with 5 pi over 2, comma 1. So that would be this very next maximum right here. So if I plugged in k equals 2, I'd go ahead and get the next maximum. K equals 3, I'd get the next one. Even if I go ahead and start plugging in k equals negative 1, then it's going to go ahead and start giving me maximums in the other direction. Okay, so that's all those are. They're formulas designed to help you find those items. Is everybody okay with that? Does anybody have any questions? Okay, what else we got here? Let's see. We have, it is continuous, so that means for every value of x, there's a corresponding what? Y value, that's exactly right. So in this case, for every radian measure, there's a corresponding ratio. You plug in any radian, you're going to get a ratio. You're always able to get an ordered pair. They're bounded above and below by the maximum and minimums that we already mentioned. Okay. It has odd symmetry. Now what this means is that it's symmetric with the origin. So let's stop for just a second. Let's make sure we know the difference between even and odd. Now this is something that we'll get into a lot more detail in the second semester. For right now, all we have to do is know what's happening graphically. You see these right here where it says f of x, f of negative x? That's how you would do it algebraically by hand. Don't worry, I'm not going to show you that right now. Okay. So let's talk about an odd function. It's symmetric with respect to the origin. Well, let's say I give you this one right here. Okay. Does anybody recognize that parent? It's x what? Not squared. Cubed. That's x cubed. That's the cube parent. Okay. So this is going to be symmetric with the origin. What that means is that it has rotational symmetry. If you can take a graph and rotate it 180 degrees, only half a rotation, okay, something's going to happen. So imagine this were like a propeller on a plane. If I were to go ahead and just rotate it halfways, what's going to happen? Like this point right here, say I rotate it clockwise, where's it going to end up? There you go. And like this point would become that other one's image. So what's going to happen if I were to spin this 180 degrees? It's going to look like I didn't do anything to it. That's what rotational symmetry is. So I can do that with sine. If I spin it 180 degrees, it's still going to look exactly the same. Okay. Now let's talk about even. Let me go ahead and give you an example of an even, which is what cosine is going to turn out to be. So now what is this right here? That's x squared. That's your quadratic parent. Okay, so if it's even, that means it's going to be symmetric with respect to the y-axis. So if I were able to go ahead and fold along the y-axis, if the two parts come together perfectly like mirror images, that's even. That's what we're talking about. Okay. Now, mathematically, we say they coincide. You know what you did Friday night when it rained? Coincide. Yeah, I'm getting big laughs today. Okay. That's okay. All right. And then you'll recognize these at the bottom. These are the 5 points that we determined ourselves for the original graph. These are what we're going to refer to as our key or critical points. These are super, super important because we're going to be using these to go ahead and transform those functions. Okay. So that's sine. Are there any questions about sine of theta? I don't know what that means. That means no? Okay, so there we go. All right, so let's take a look. Let's do the same thing for cosine. So sine and cosine are going to have the same period. Now we're talking about their parents. It's going to take 2 pi radians before it starts to repeat again. But unlike sine, cosine is going to have a more curvy shape to it like this. I always refer to it as a curvy V shape. So this is what one period of cosine is going to look like. Okay. Now to see why, again, we're going to look at the unit circle. Okay. All the same information. You'll notice I have the same quadrantal values, 0, pi over 2, all the way to 2 pi. But now we're evaluating these at cosine. So somebody help me out. Cosine of theta, that was x over r, right? But we're on the unit circle, why? Because the radius is 1. Yeah. So again, that also emphasizes why last week I said cosine is your x variable. Okay. So at these locations, these radian measures, all I'm interested in are the x values. Okay, so somebody help me out. What's cosine of 0? Oh, not 0. That's sine of 0. Remember, cosine is x. So what's the x value from that ordered pair? 1. So at 0 radians, I have a ratio of 1. Okay, and let's rotate around. Cosine of pi over 2. Okay, so here's pi over 2. Here's the ordered pair. So what's cosine of pi over 2? What's the x value from that location? That's 0. So now I have a second one. Pi over 2, 0. Is everybody okay with what I'm doing? So somebody help me out. What's cosine of pi? -1. So pi is -1. There we go. What's that? Oh yeah, go for it. What's cosine of 3 pi over 2? That's 0. So that would be 3 pi over 2, 0. And then finally, I need cosine of 2 pi. Well, remember, 2 pi is coterminal with 0, so that should be what? 1. See, this is where it starts to repeat again. That's why they're periodic. So 2 pi will give me 1. Everybody okay with how I created those? Okay. Oh, hold on one second. Oh, there's a line, so as soon as it's available, I can't let you go just yet. Sorry about that. Yeah. It'll go quick. It'll go quick. What's up? Well, the radian measures are going to change, but these y values are going to remain consistent. And see, the further out you go, because past 2 pi, then you got to have angles beyond 2 pi because that represents a second revolution. But yeah, okay. So let's see. We got 0, 1. So while sine starts at the origin, cosine starts with a maximum. And then we have pi over 2 comma 0. So pi over 2 comma 0, pi -1, 3 pi over 2, 0, and then 2 pi 1. So there are the 5 points that we just created. And there's my curvy V. Okay. There we go. Now remember, just like sine, that's one revolution on the unit circle. Okay, let me go ahead and get this out of the way. So right here, see, I'm color coding it right there. So that one revolution in blue, there's this one part of the graph. If I rotate a second time, well, it's going to go ahead and give me another period of the graph from maximum to maximum. Okay. I can rotate it an infinite number of times. I can create an infinite number of periods. If I rotate clockwise, that's going to go ahead and give me the same graph on the other side. Questions? Now the points are going to have the same names. We have a maximum. We have a minimum. Okay, here's another maximum. What do you think these two in the middle are? Those are zeros. There you go. Okay. There we go. It's just a new type of graph. Okay, you plug in angles, you got a ratio, you got your points. Okay. All right. Now, we're going to be able to go through this a little quicker. Okay, so the domain is all reals. The range is still from -1 to 1. Okay, because the graph is infinitely wide, x-intercepts, maximums, and minimums, you're going to have an infinite number of those. Okay, so each one of these, you have a formula here that'll go ahead and help you find any maximum, any minimum, or any x-intercept that you want. Okay, the y-intercept is 0, 1. It is continuous. It's bounded above and below by the maximum and minimum. We already said cosine is going to be even. That means it's symmetric with the y-axis. And then here are your key points. Those are the 5 quadrantal points that we just created. Okay. Right, Lexi? Right, Lexi? Right, Lexi? Right, Lexi? Right, Lexi? This is going to be the fun part of the recording. Right, Lexi? Say right. Right. Okay, there we go. Fantastic. Okay. Well, now that we know a little bit about what sine and cosine are going to look like, let's start getting into some features here. Because remember I said, bless you, our goal was to transform these. This is what we want to get to. A sine of bx plus c plus d, a cosine of bx plus c plus d. Okay. A represents your vertical dilation. B represents your horizontal dilation. Okay. C represents a horizontal shift, and D represents a vertical shift. Each one's going to have its own name, and we're going to look at each one in part. Okay. But let's do a quick review because it's been a while since you probably talked about transformations. Okay. What's a dilation? Like it said that your pupils dilate. What does that mean? Yeah, does pupils get larger or smaller occasionally? That's what happens to your graph. When we dilate it, we're changing the size or the shape. Okay. Now, how do we know there's a dilation in a function? What operations are you going to use? Multiplication, or by extension, division. So if you're multiplying or dividing, it's going to be a dilation. Okay. Now, when you're talking about a shift or a translation, so let's say, we just have like sine. All we're doing here is just shifting it left and right or vertically in your grid. Okay. Well, how do I know that's happening? What two operations am I using? Addition and subtraction. So if you're adding or subtracting in your function, then you're going to have a translation. And what's the one little item responsible for the reflection? A negative. A negative's one job is to reflect. That's it. Man, there must be a sick girl in the bathroom here. There you go. Carla, you're good. All right. So we're going to go ahead and start this with amplitude. We can change the height or the amplitude of the graphs of sine and cosine by transforming the equation of the function. Make sure she gets her. This will change the range of the parent function. Okay, so let's say we want to graph y equals 2 sine of x. Okay. Now, I strongly encourage you to go ahead and do this, especially since a lot of people are learning this for the first time. I would encourage you to graph what's called the pre-image. That's the parent function before any transformations. You always draw that as a dashed curve. Okay, so for sine, forget about the 2 right now. Okay. Remember, sine starts at the origin. So we had a 0, then a maximum, a 0, a minimum, back to a 0. So this is what the graph of sine looks like. We just sketched it a few moments ago. There's one period. And you don't have to do this, but I really think it's going to help a lot of people out. The more familiar you are with sine and cosine, the easier the other trig functions are going to be. Trust me on this. Okay. Now, let's go ahead and draw what's called the image, 2 sine of x. Well, how is the 2 connected to that sine? It's multiplied, right? So what does that mean? Is that a dilation? Was that a shift or a reflection? That's a dilation. So the shape of this graph is going to be changing. Okay? But you got to be able to answer one more question. Is this horizontal or is this vertical? Let's take a poll. How many people think it's horizontal? How many think it's vertical? How many people are not going to vote? Okay. It is vertical. The reason being, unless it is directly connected to x, it's going to be vertical. Okay. And I'm going to kind of expand on that tomorrow. So all I want to do is just take any ordered pair that we have here, like xy. We're going to stretch it vertically by a factor of 2. So every ordered pair is simply going to become x comma 2y. Did some of your previous teachers show you how to go ahead and transform the ordered pairs to help you out? Maybe, maybe not. Okay, that's okay. That's okay. So can anybody tell me, are there any points here that are not going to change? There you go. These points here, the x-intercepts, they're going to stay exactly where they are. Let's see why. Let's take one of these. Like, for example, pi comma 0. Okay. So this is my original point. Remember, this is how it's being transformed. Well, the x value is staying the same, but what am I doing to the y values? I'm doubling them. But 2 times 0 is still 0. So that's why those x-intercepts are going to be anchored where they're at. Okay. But somebody help me out. This one right here, what about pi over 2, 1? So pi over 2 comma 1, what would that be? Pi over 2 comma 2, because 2 times 1. See, the x's, nothing is happening to them. It's only the y values that we're doubling. So this will now be at pi over 2, 2. What about 3 pi over 2 negative 1? 3 pi over 2 negative 2. And now we go ahead and connect that with a smooth curve. So it's going to look just like this. There we go. So the pre-image is the original parent. That's dashed. The image is your final answer. Your final transformation is a smooth curve. There you go. Okay. So let's take a look at 3b. We're almost done. I know, I'm sad too. So let's start. Don't worry about the negative 2. I just want cosine. The cosine start with a 0 or a maximum? Maximum. So 0, 1. So we had a maximum, then a 0, then a minimum, then a 0, and then a maximum. Okay. Remember, cosine had that curvy V shape to it. Okay, so it's going to look something like this. There we go. Again, if you feel you're not needing to draw that pre-image, fantastic. If you think it'll help, I would encourage you to draw. Okay. So what's happening and where? Okay, so the negative, now is it going to reflect with the x or the y-axis? Okay, so this is going to reflect over the x-axis. Now that's all the negative is going to do. So it says negative 2. You actually want to look at that as 2 transformations. The negative is the reflection. What do you think the 2 is going to do? It's going to do just like the previous one. It's going to vertically stretch it by a factor of 2. So we're going to vertically stretch it and then flip it. So every ordered pair xy on this one is simply becoming x negative 2y. Okay. And now normally I'd give you about a minute to go ahead and try this, but we'll go ahead and just do this together since we're almost out of time. Are there any points that aren't going to move? Yeah, those zeros, 0 times a negative 2, that's still 0. Okay. But what about this point right here? It's at 0, 1. Where would it go? 0, 1 would become 0, negative 2. Yeah. What about this point at pi negative 1? 2. And then for 2 pi comma 1, that would be 2 pi comma negative 2. So see, there's your still curvy V shape, but it's been stretched by 2, and it's been flipped. There you go. Now, this leading coefficient A that's responsible for that vertical dilation, that's what we're going to use to find the amplitude. So the amplitude is the height of the wave, not the height of the function. Okay? So if I'm looking at the function, see, it goes from -2 to 2, so it has a height of 4. But we're only talking about the height of a wave here. Okay? So for both of these, the amplitude is 2. And it's super easy to find. All you have to do is take the absolute value of that leading coefficient A. That's your amplitude. Okay. Questions. Okay. Will this stuff be on the test Thursday? No. We got to have time to practice it. Okay. So there we go. We are done. Let me go ahead and get this settled.